So let's have a look at this application of calculus to the physical world. I guess one of the first applications that it was used for, that being motion. So let's define a few things. We talked a little bit about this yesterday. Displacement. We often just use x for displacement. It could be any pronumeral really, but x, I think in physics they use s. So yeah, they use s sometimes. And it's basically distance from a point, but with direction. So velocity. Now velocity is similar to speed, but with direction. So rate of change of displacement with respect to time. Remember, speed would be the rate of change of distance with respect to time. So the difference being, again, direction. Some different symbols, obviously v for velocity, but as it is a rate of change, we could just put dx to t. When we're talking about motion, a notation we use for the derivative is just a dot. And so you might see x with one dot on top, which just means the first derivative with respect to time of x. And the third component that's very important is acceleration. And that's the rate of change of velocity with respect to time. Now, this is the unusual one because whilst you can say displacement is distance with direction and velocity is speed with direction, acceleration is acceleration with direction. The same word gets used for both. So acceleration, when we're talking about it, we're meaning the one that does have direction. We'll say which direction's in. So A seems a logical one for acceleration. Could be the v to t, because it's the derivative of velocity with respect to time, but then we could say it's the second derivative of displacement with respect to time. So we could have x with two dots, we're saying two derivatives, or velocity with one dot. So they're all different notations that we could use for acceleration. Now here's an important thing. Deceleration, or slowing down. Put it out of your mind. There is no such thing. Okay? Right. Slowing down is simply when acceleration is in the opposite direction to velocity. Right? So you still have acceleration, but it's just in the opposite direction to which you're traveling. So if you imagine acceleration like a force, because force is mass times acceleration, so it's like someone's pushing you or pulling you back. Well, if it's in the same direction in which you're travelling, that means they're pushing you, you go faster, or what we call accelerate. If their acceleration is in the opposite direction, then it's like they're pulling you back. So you'd be travelling in a certain direction, they'd be pulling you in the other direction, so you slow down. And that is what we think of as deceleration, but it's just acceleration in the opposite direction to which we're travelling. So whenever you see the sign of velocity, and it's opposite to the sign of acceleration, you're slowing down. If they've got the same sign, they're speeding up. Even if they're both negative, right? Negative has nothing to do with size, it's direction. So you can still be going faster even though you have a negative velocity or a negative acceleration. Okay, here's just a little flow chart here I saw in a newspaper once and I thought it was nice. So I'll share it with you. There's the three main things. Oh, look, to go from there to there, you differentiate. And to go from there to there, you differentiate. But if I want to go back the other way, we integrate. And then if I want to go from accelerate, it was in a newspaper. It was good. Okay. Here we have a displacement time graph. It is a displacement time graph because, look, we have negatives here. So I know it's not distance time, it's displacement time. Now, yesterday we talked about average velocity, but average velocity is not that useful. You know, like a policeman can't pull you over and say, your average velocity for the last 10 kilometres has been this, I'm going to book you. No, they have to book you on the instantaneous velocity that you're travelling. Okay? Unless you've got those funny ones where they have a camera here and a camera here and those bridge cameras they have. But anyway, normally it's they've got their radar, bang, and they take the instantaneous velocity? Well, as it is the derivative in relation to our graph, it must be the slope at a particular point. So if I wanted to find the velocity, I could use my displacement time graph, and I just draw in the tangent at that particular point, whatever the slope is, that would be the velocity. And then I could do a similar thing for acceleration. Now, if that's my displacement time graph, I could draw a velocity time graph on that. Now remember, when the curve's going up, we're increasing, we know the derivative, or in this case, velocity is positive. When it's going down, it's negative. When it's stationary, then velocity must be, that's kind of cool when you think about it. When velocity is 0, it's stationary. Anyway. So we get that sort of shape. And if we actually look at the shapes of the graph, that kind of all ties in nicely too, because that sort of looks like a cubic. When I was up and down cubics, differentiate a cubic, you would get a quadratic, and that looks like a parabola. So if I wanted to find the acceleration at a particular point, again, I could draw in the tangent to the velocity graph, and that would, the slope of that would give me the acceleration. And if I wanted to draw the acceleration graph, then I could do a similar thing. I'll now draw the slope of this graph, or I could use the concavity of the first graph. And, well, if this is a parabola, then I'm expecting straight line, yeah. And so it actually ends up being something like that. Okay, so we're going to work out, first of all, the distance travelled. So the distance travelled, I'll look at my displacement graph, I've gone up to 2, down to -2, then back up to, I think that's meant to be -1 there. So all up, that's 7 metres I've actually travelled. As opposed to my total displacement, how far have I travelled in relation to my starting point? It's -1. So I've travelled 1 metre, but in the negative direction. So the opposite direction to which I started travelling. Average speed. So average speed would be 7/4, distance over time. And average velocity would be total displacement over time. So we've got -1/4 metre per second. All right, here's an actual equation for one of our graphs, because the nice thing is we don't actually need the graph, because that's the beauty of the calculus. Calculus tells us how to find those important points, the stationary points and things like that. If we've got an actual equation of the graph, we can just use that. And in this case, it's a cubic. So displacement is t cubed minus 21t squared, it works out to be. We're going to find the acceleration at time t. So in other words, if that's the formula for displacement, what's the formula for acceleration? Well, all they're really saying is, hey, differentiate this twice. That's all the question's saying. So velocity, differentiate at 1. Acceleration, my second derivative. So there's my formula, 6t minus 42. So now they want to know when it's stationary. And so now we can think of it two ways. We could say, well, it's stationary when the first derivative is equal to 0. Or if we're thinking about motion, it's stationary when the velocity is 0. And obviously it gives us the same thing. So it's going to be stationary when the velocity is 0. Solving that little quadratic, we get two possibilities, t equals 0 and t equals 14. Now, this can sometimes cause problems because people think, hang on, how can you start off and you're stationary? Because surely if I start and I'm stationary, then I'm not going to move. But that all then comes down to acceleration. Yeah, if I started and I was stationary and the acceleration was 0, so no force is being applied upon me, I'm not going to move. But if I'm stationary, but I do have an acceleration, that means some force is being applied, so I will move. It's like I'm standing there and someone's either going to push me in the back or pull me back. So I would move. So in this case, it is stationary initially, and that's the fancy word for t equals 0 when we're talking about this stuff, initially. And after 14 seconds. All right, so our particle is moving on the x-axis, a very convenient place for it to travel, because then we can just locate it nice and easily. Again, it's starting from rest in this case, and but it's starting at x equals 7. It's not starting at the origin. It doesn't have to start at the origin. It can start anywhere it likes. Its acceleration is given by 2 plus 6t. We now want to find where it is when time is 3. So, okay, we know a formula for acceleration. This is where it becomes really important to remember plus a constant. Because if you forget plus a constant in this sort of problem, it can throw out, obviously, your answers when you want to work out velocity and so on. So we've got 2t plus 3t squared. There must be some information that links time and velocity, and that is we've started from rest. So subbing in t equals 0, v equals 0, c equals 0. So you would have got lucky if you forgot the constant in this one. But c is not always going to be 0. So there's our velocity. Integrate again, we get t squared plus t cubed. Again, we've got something that links time and displacement. T equals 0, displacement is 7. So this time the constant is not 0, so we'd be in trouble if we forgot it. Constant is 7. We now have the three equations that allow us pretty much to solve any motion problem: acceleration, velocity, displacement. We want position, so we want displacement when t is 3. So subbing t equals 3 into our last formula we worked out, we got 43. Notice the way they worded this question is they said find its position, because theoretically if they had said find its displacement, they'd have to say displacement from where, because it didn't start at the origin. It started at 3. So, no, it started at 7. So technically its displacement from its starting point would not be 43. But that's just, you've got to be careful with that. I remember having a lovely little argument about this HSC question 2 years ago. But anyway, I'll show you it later. No, so you'll see what I mean. Here's the 2001 question. So here's an interesting path of a particle. X equals t minus 2 on t plus 2. What does this tell you about the particle straight away? It can never be at negative 2 seconds. I suppose that makes sense. If we're starting at 0, it'd be a bit hard to get to negative 2 because you can't have 0 on the bottom of the fraction. Okay. What's its displacement when t equals 0? So in other words, where does it start? And it starts at negative 1. So displacement, or the particle is 1 metre to the left of the origin. So you can say it's at x equals negative 1, or like I've done here, is actually physically describe its position. We tend to think of the number line in the traditional way. So if it says negative, we say, oh, well, the left of the origin, positive, the right of the origin. Show that. Now, this probably would have been in a 2-unit paper. Hopefully for us, oh yeah, that's sort of kind of a little bit easy. All we're saying is do a very simple polynomial division, I suppose, t minus 2 divided by t plus 2, but they're trying to give them a big hint that, hey, writing it this way will help us later on in this question. So hence find the expression. So, all right, well, 1 minus 4 on t plus 2, if I do an algebraic fraction, oh, look, it's t minus 2 on t plus 2. So yes, indeed, we can write displacement as 1 minus 4 on t plus 2. So to find the velocity, we'll differentiate that. Well, obviously the 1 goes to 0. Then I've got to I'll use my reciprocal rule, minus the derivative on the function squared. So I get minus 1 on t plus 2 squared, or minus 1. So we have 4 on t plus 2 squared. There's my velocity. Acceleration, I can use it again, minus the derivative on the function squared. Or I suppose this one might be easy just to turn into index form and do it that way. Whatever your preference is. But anyway, we end up getting acceleration is minus 8 on t plus 2 cubed. So we have the 3 main expressions we need. Is the particle ever at rest? And then the bit that you guys often hate, give reasons for your answer. What? Write words? This is in English. So there's our velocity formula. Is it ever at rest? Be brave now. You got a 50-50 chance here. No. And that's why they say give reasons for your answer, because yes, you do have a 50-50 chance. Why? Yeah. We've got a fraction. There's a constant on the top. Well, 4 can never equal 0. So there it is. So that particular expression can never equal 0. So therefore the particle is never at rest. What is then the limiting velocity? So limiting velocity just means as time approaches infinity. So what's happening to this particle? It's never stopping. So poor thing's going to get tired, but it just never stops. So in other words, what is the limit as t approaches infinity of v? So the limit of 4 on t plus 2 squared. All right, what's the limit of that? 4 on t plus 2 squared. 0. So whilst it never stops, its limiting velocity is 0. So it'll slow down. Another way of thinking about it is we can think of the graph. If I was to draw 4 on t plus 2 squared, we can see it's going asymptotic down to the t-axis in this case. So it's getting closer and closer to a velocity of 0. So there we go. There's our limiting velocity. 2002 question, later in the paper, 8b. So again, we're moving in a straight line. We do that a lot. Time t seconds, distance x meters from a fixed point. Oh, a bit of trig. X is sine 2t plus 3. Reality is it's simple harmonic motion, but you can't use that word in 2-unit, right? Because they don't do simple harmonic motion. Sketch the graph. Okay, so we're just sketching a trig function. So I know the amplitude's 1. I've shifted it up 3. Period would be 2 pi on 2, so it's pi. I'll mark my divisions off every pi on 4. They want me to go from 0 to 2 pi. So, okay, there's my axes. Haven't bothered with negatives because they've said 0 to 2 pi. So let's plot it in. Shifted up 3. A sine curve normally starts at the origin, but we've shifted up to 3. So there's my first point. Then it goes up to the amplitude, down, up, down, up, down, up, down, and whee, there we go. There's our graph. Okay. Using your graph, or otherwise, find when the particle is at rest. So all those stationary points we're looking for. So the graph, if you're drawing the graph accurately, that's going to be quicker, I guess, than using calculus. But we know it's when velocity equals 0. So I could go and solve dx to t is equal to 0. In other words, the stationary points. So I haven't bothered. I've just looked at the graph. I noticed, okay, we're at pi on 4, and at 3 pi on 4, and 5 pi on 4, and 7 pi on 4, there's all the times that it's stationary. Describe, another one of those word questions. Describe it completely. Okay, let's go crazy. Well, my particle oscillates. Oh, there's a good word for simple harmonic motion. It's going backwards and forwards, backwards and forwards. Oscillates. It oscillates between x equals 2 and x equals 4 with a period of pi seconds. I reckon that describes it completely. Yeah, it's a pretty good description, I thought. All right, 3B. Yeah.